All right, so we're recording for Liesl as she is setting. This was the deal. Liesl is. I told her I would record this lecture if she set a PR in her event. So she should be jumping pretty high today. So.
Wait, wasn't her record 5.7? Her PR 5.7? I just remember it's that's how
So she needs to go to. Is it done by inches or is it like how much do they raise the bar?
Oh, like the increment?
Yeah.
Probably quarter inches?
Quarter inches?
Maybe?
Okay.
We can ask.
Yeah, we'll have to find out. Yeah.
Yeah, on the she'll comment.
Okay, so we're going to talk about phase diagrams, and in order to do that, I want to look at first, just as a reminder, dg in terms of its natural variables are vdp minus sdt, right? Okay, so let's just, again, sketch out a quick phase diagram so that we can see. We're going to look at a pressure-temperature phase diagram. And looks like this. Okay, and the phases, this is solid over here. This is liquid. And then this is gas. And then sort of up here in this quadrant over here, this is a supercritical fluid. All right, so up here, this is the critical point. The liquid gas curve actually stops. And that's actually kind of just interesting, all by itself, because you can actually turn a substance from a liquid into a gas without ever going through a phase change. And the way that you do that is you start over here and you go around the critical point. So you start here, you increase the pressure, then you can increase the temperature, then you can decrease the pressure, then you can decrease the temperature. And you can get from a liquid state to a gas state without ever going through a so-called phase transition, in the sense that there's like a phase boundary, right? Where you can clearly see the difference between the liquid and the gas phase. The reason for that is because liquids and gases are both unstructured, random movement of atoms and molecules, right? So the difference between a liquid and a gas is one of degree, not of kind, right? So a liquid, all the molecules or atoms are moving, and they're really close together. In a gas, they're farther apart. That's the only difference. So there is no such sort of way to go from a liquid to a solid without going through a phase transition. Okay, so what I want to do is look at what happens to G as you move across this. So we're going to start like here. We're going to increase temperature. And we're just going to go straight across. So if I drew this exactly horizontal, we wouldn't be changing pressure, okay? So what is happening to Gibbs energy as you move across this diagram, as you start from this low this low temperature, and you're going to a high temperature? Would it increase? That's a good question. Is it increasing or decreasing? That's a good question. To answer this question, we want to ask ourselves, what is partial of G with respect to T at constant P. Right? So let's just, again, remember these partial derivatives just tell about how stuff changes, right? So this partial derivative tells me that how does G change as I'm changing temperature and I'm holding pressure constant. So what's the verdict? What does this partial derivative equal? Liesel, you can chime in any time now. So we want to look back at this full differential, right? So dg equals something dp plus something else dt, right? Well, no, that just means p is being held constant. It doesn't mean this partial derivative is 0. It just means that I'm moving horizontally across this graph.
The change of t, the bigger that is, the more you're taking away. Is that right?
So as you increase temperature, so the question is, what happens to Gibbs energy as you increase temperature, right? So we look at this equation and we say, well, dg is equal to the partial of g with respect to p at constant t times dp plus the partial of g with respect to t at constant p dt, right? Remember, these two things, like volume and negative entropy, those tell you what the partial derivatives are. So this is negative s. You see that? Because the derivative, yeah, because you're taking it with respect to t, holding p constant. Now, if you want to sort of think about this more algebraically, you can divide both sides by t, hold p constant, so that term goes away, and you're left with just negative s. Right? So all those rules of algebra still work for differential equations, even though it's like technically wrong. Okay. All right, so what does this tell me? This tells me that if I'm changing temperature with constant pressure, that G is going to change where the slope of that is negative S, negative the entropy. Okay? All right, now let's think a little bit about this. Is entropy ever negative? So no, it's never negative. Entropy is never negative because the entropy of a pure crystalline substance at absolute 0 is 0. You can't get less than that, right? So entropy is always, it's inherently positive quantity. So what does that mean about this slope? Is this slope dg dt, is it positive or negative? It's got to be negative because I have a negative of a positive number, which is negative. So if I want to graph out g as a function of t, right, then I'm going to get negative s. Okay, so before we do this, we're going to sketch it out sort of qualitatively. But let's drop a couple of these phase boundary lines so that way we know where the phase boundaries are. Okay. So what has the highest entropy? Solid, liquid, or gas? Gas does, right? So in this graph, I'm going to expect gas to have the steepest Gibbs energy change. It's going to look like that, right? And then liquid is going to be not as steep. And then solid is going to be the shallowest, right? Okay, now I have drawn these so that you can see that the liquid curve, like this liquid part right here, it continues, right? But we'll put some dotted lines there because what does Gibbs energy want to do? Does Gibbs energy want to seek a minimum or a maximum? A minimum, right? So let's just say that I am cooling some water down. So here I am, I'm right here, I'm cooling water down, and I cool it down below the freezing point, but it's still a liquid. Have you ever seen a demonstration of this before? Where you get a liquid and you cool it below its freezing point? Do you know this is possible? Yeah?
When you have there's like a trend where you have a water bottle in the freezer, and then it's like you take it out, it's still liquid, but then like hit it.
Yes,
and it turns out-
exactly that, yeah. And it will suddenly crystallize, right? So what's happening there, right? Well, Gibbs energy seeks a minimum. That doesn't mean you can't be up here, right? So you can actually be here. You can be in a liquid state below the freezing point. But any small, like, little disturbance will cause it to spontaneously freeze, right? So that's called a super cooled liquid. It's where you get the liquid cooler than its freezing point and it stays liquid. I actually did some work on this in graduate school because we were measuring the kinetics, the heterogeneous oxidation of aerosol particles. So we took some particles that were like, so they were oleic acid. And no, we did oleic acid, but we also did, what was it called? Stearic acid. That's what we did, stearic acid. And we cooled them down, and we were able to make super cold droplets and measure the kinetic. No, it was oleic acid. It was oleic acid. We were able to make super cold droplets of oleic acid, and then show the kinetics of it, whether they were solid versus super cooled. It was kind of a neat little project. Okay, so all right. So Gibbs energy seeks a minimum. So if you wind up going over here, you can get a superheated liquid. It falls down, right? You can get a super cooled vapor or a super saturated vapor, right? It will condense. All right. So now we want to look at what happens as we increase the pressure. So if we increase the pressure, we're going this other way, right? So we're going to go this way. I have to kind of draw it crooked to show what's happening. So we're going to increase the pressure, holding temperature constant. Oops. P, there we go, holding temperature constant. So what does this partial derivative equal? Equals V. So what will my slope be? Will it be a positive or negative? Positive, because volume is always positive. You can't have a negative volume. You can have a negative change in volume, but you can't have a negative volume. Just like you can't have a negative mass. Right? What would that mean? Negative, like kilograms? What? You know? Okay. So we can look at this as well. Going to look at G versus P. Okay. So first, at low pressure, you're dealing with a gas. What's the volume of a gas? Is it big compared to that of a liquid, or it is big, right? A gas is very big. So you're going to have a steep curve for the gas. Then when you get to the liquid, it'll be like this. And then the solid, be, pretty much the same as the liquid, right? Solids and liquids have very similar densities, so you'll have like a phase transition there. So up here, this is your gas, this is your liquid, this is your solid. Down here, it's the reverse. Except for water, these two are swapped. For water, you go from a gas to a solid, then to a liquid, because most phase diagrams, the solid and liquid curve here has a positive slope. It's very steep, but it's positive, so it's kind of tilted this way. So you can go up through the liquid to get to the solid vertically, but water is tilted this way. So you would go from a gas to a solid to a liquid. Water is a curious substance. So this order may be different. It's never the case with this. When you increase temperature, you never go through a liquid first to a solid. It's always solid, liquid, gas. Okay, so one more thing that I want to point out here is that at these phase transitions, the Gibbs energy of the liquid here is equal to the Gibbs energy of the gas. This means that at the phase transition, you're at equilibrium. So if you move away from equilibrium, you move just to the right a little bit, you increase the temperature, or move to the left a little bit, you decrease the temperature, then you're going to, the system is going to want to either turn all gas or all liquid, right? Okay. So that's a little bit about phase diagram. Any questions? I forgot, do you guys have questions about the homework too? You do have questions about the homework. Okay, well, this is a good time to ask them because we're about to move on to binary mixture phase diagrams. So, Liesl, do you have any questions? No? Okay. Wouldn't that be funny if I was like, Liesl, do you have any questions? And my computer started talking to me. I think I'd wet my pants. I'd be like, I'm out of here.
Define a question.
Define a question?
Mine is just like I'm lost.
On all of them?
No, not on all of them. On
The last three?
yes.
So let me just point out like some rules on partial derivatives, because this is one of the things you have to be able to do. Are you taking it with respect to t? Partial ln of q with respect to t?
Respect to v.
With
Well,
respect to v?
The one of them's with respect to v. The other two are with respect to t.
Okay, it doesn't matter. We'll just, it doesn't matter. We just do it like this. Okay, so with these kinds of problems right here, when you're taking the partial derivative of a natural logarithm, q is going to be a function of t times a function of other stuff. Okay, so I think in one of them it's like, it's like t to the 3/2 or something, and then you've got a whole bunch of other things in there, right? So you've got like, I don't know, Boltzmann's constant. Is there volume in there?
There's like 2 pi.
2 pi. Okay, 2 pi. M. Is M upstairs?
Yes. And then is it? Yeah. And then h squared. Is this supposed to be h bar?
I don't think so. That's what the 2 pi is there for.
Yeah, and then h squared on the bottom.
H squared. Yeah, let's just throw some other stuff in there. Volume. Let's put a volume term in there. Let's put, I don't know. Here's some other letters. A and B are in there as well, right? So it just gets really complicated, right? Okay, so guess what? This is your function of t. All this is your function of other stuff. Okay? So whenever you take the natural log of q, you get three halves ln of t plus ln of other stuff. I don't care what the other stuff is. It's the rest of that garbage, right? Now watch what happens. When I take the derivative of both sides, with respect to t, the first term, I'm going to have the partial with respect to t of 3/2 ln of t. Okay, so we're not going to actually do that yet. Just want to point out. Are there any t's over here? So what's the partial derivative with respect to t of this other stuff? 0. So everything else that's in Q just suddenly vanishes, right? Because I'm taking the derivative with respect to t. Okay, so now we got to worry about this. So I guess this should help simplify those, right? And then you need to take the derivative of this. Are you stuck on this part too? Like, how do I actually take the derivative of that? Let's write it in more familiar notation, okay? Let's do this. Okay, let's let y equal 3/2 ln of x. Then if I want dy dx, well, my 3/2 is just 3/2, right? And then I have the natural log of x. Well, what's the derivative of the natural log of x? It's 1 over x. So this guy right here is 3 over 2t. So once you get that, then you can start putting this stuff up into the other equations, right? Where you've got CV is the partial of u with respect to v. So that one you're taking with respect to v. Or no, you're taking with respect to t on that one, CV. Anyway, so that big partition function looks scary, but most of it belongs over here in the other stuff, and it goes away. Does that kind of give you enough direction to kind of get going on those? Okay. Okay. Is that the last three, or all that? Essentially? Okay.
And then it's like, you calculate the heat capacity in terms of K.
Yeah, so you're going to have a K. All the Ks are KBs. So I think some of them are missing the subscript B. So if you see a lowercase k, it's KB. And capital Q and lowercase q are the same. So you can make that substitution.
When it says like calculate in terms of kV, that's when we take the partial derivative of the heat capacity over kV.
Well, you'll still have KB in your answer. That's all. That's all that means. You're going to have KB, some numbers. You might have a T in there, depending on which one you're going for. I think the heat capacity doesn't have a T in it. It's just going to have KB and some numbers. And then what was the one with where you're taking it with respect to volume? Are you solving for like pressure or something?
The pressure macroscopic system.
So you're solving for pressure there. So there you're going to have like, N. Well, yeah, you might have N. You'll have K. I think you should end up with I don't remember if that one's ideal gas or a different one. It might be the ideal gas. Now, the ideal gas law, remember that R is equal to N in AKB, where N is Avogadro's number. And KB is Boltzmann's constant. It's in units of joules per Kelvin. This is per mole. So if you crunch that, what do you get? It should be like 8.314, yeah. Which is the ideal gas, or the gas constant R. So there's actually no, the difference between big R and Boltzmann's constant is big R is a per mole, and Boltzmann's constant is just joules per Kelvin. So it's sort of like a per molecule or per atom or something. If you don't ever write that down, it's just Boltzmann's constant. So the ideal gas law can be written like this. Or like that, where little n is moles. And big N is like atoms or molecules or something. All right. All right, so I want to look at a two-substance phase diagram and spend a little bit of time with this. Raoult's law is what kind of governs our treatment of this. And it says that the partial pressure of substance J is equal to the mole fraction of that times its partial pressure all by itself. So this is valid at a high mole fractions. Okay, so X is the mole fraction. And then, PJ star is just the vapor pressure of the pure substance. And for a substance or a mixture that obeys Raoult's law, you can actually write a nice diagram where pressure is on the x-axis, x2, or y-axis, x2 is on the x-axis. This is going to go from 0 to 1. Okay, so 0 means it's all component 1. So over here is all component 1. And then 1 means it's all component 2. Okay, so we know the points that this is going to be P2 star. Over here, this is going to be P1 star, right? So when I have pure component 1, I'm going to have a pressure that's just P1 star. And if I have pure component 2, I'm going to have a pressure that's P2 star. Okay? And the pressure for P2, maybe I should do these in different colors. Here, let's make this one blue. Kind of looks black now. All right, so this one, following Raoult's law, looks like that. This one, following Raoult's law, looks like this. Okay. Notice that this is a linear function, right? Let's just go back and look. Pj equals xj times pj star, right? So when xj is 0, 0, then the pressure is 0. When it's 1, then it's P2 star. And x1 goes in the opposite direction of x2 because this is a two-component mixture. So the mole fraction of x1 is 0 here and 1 over here. Does that make sense? Kind of. Because I've got, so for a two-component mixture, x1 plus x2 has to be 1. because this is mole fraction, right? The mole fraction is the moles of substance, 1 divided by the total number of moles. And then the moles of substance 2 divided by the total number of moles. So that equals 1. So the total pressure is the sum of these two pressures, right? And it is, looks like this. This is P total. So it is also linear. And we can actually obtain an equation for that, noting that P total is equal to P1 plus P2, which equals X1 P1 star plus X2 P2 star. And then noting that X1 plus X2 equals 0, I can plug in 1 minus X2. And I get this. And then if I, combine my like terms, combine all my X terms together, then we get this right here, which is and let's just pause here and make sure that this makes sense. If I just think about this as y equals mx plus b, we've got y. M is this right here. X is that, and B is this. So this is my intercept, P1. Well, that's P1. This is my slope, which is P2 minus P1. Well, is that the slope? Let's look. P2 minus P1 divided by, 1. Right? So the rise over the run, that's your slope. So this is just the equation for a straight line, and that's what that is. Okay, so far so good, right? All right, now we want to look. So this is all based on the liquid composition. So X2 is the liquid composition. Like if I mix two liquids together with that mole fraction. Okay, so what is happening in the vapor phase? We're going to use Y for that. So Y is the mole fraction in the vapor phase. Right? And if you're not convinced of this, we can just throw in the ideal gas equation of state, where we have Yj equals Nj RT over V, Nt RT over V. So what survives? So the RTs cancel, the V's cancel, and I'm left with Nj over Nt. This is the number of moles in the gas phase of component J divided by the total number of moles. Right? So that is the gas phase mole fraction. Well, if I substitute in Raoult's law, Pj is just Xj Pj star over P total. Now, this would all be nice if P total were constant, wouldn't it? Because then I would just have like yj is just equal to xj times a constant. So they would be, essentially another linear function. But is P total constant? It's not. It's changing. So P total changes from P1 to P2. So that's actually changing. So for this two-component mixture, so this is just in general, for our two-component mixture, I have x2 P2 star over I've got this. Now, is this a linear function? It is not. All right? So remember, x is our mole fraction. That's our independent variable. So we're looking at how y changes with x. x2 is upstairs and it's downstairs. And it doesn't cancel, right? Because I have an addition term here. So it doesn't cancel. So this is a nonlinear function. So we can't draw just a nice straight line to connect them. Qualitatively, what this looks like is this. Let me sketch out another pressure versus Z2. We're just going to use Z for like the total mole fraction. And what you get is we get that. And this. So this is Y2. And this is X2. Okay, all right. So we get a nonlinear mole fraction in the gas phase. Okay. So let's go ahead and label this to figure out what's what. So what's down here? Is this gas or a liquid? It's a liquid. Yeah, because if you want to make it a liquid, you want to reduce the pressure as much as possible, right? And reducing the pressure would turn like a gas into a liquid. Is that right? Does that sound right to you? If you want to turn a gas into a liquid, you would give it less pressure. You'd expand it. Give it more pressure. That's right. Down here, you've got, this is gas, right? Up here, this is liquid, right? And just to reiterate from our phase diagram, right? If I want to turn something from a gas into a liquid, I have to go up in pressure, right? I want to go up in pressure to go to a liquid. Okay, so what's in between here? It is not supercritical. It is simply a biphasic region. This is a liquid plus gas. So this doesn't exist on, well, okay, I mean, so for a pure substance phase diagram, the biphasic parts of the phase diagrams are lines, right? If you're on this line, you can have both liquid and gas present. If you're on this line, you can have both liquid and solid present. If you're down here, you can have solid and gas present. If you're right here at the triple point, you can have all three present, right? So there aren't regions on the phase diagram where you can have two phases. There are lines on the phase diagram where you can have two phases. With the two-component and multi-component mixtures, there are regions where you can have biphasic mixtures, right? So there's a range of pressures over which you can have your liquid and your gas present. Probably the best example of this with pure substances is the volume, right? So when you look at the volume phase diagram, you have that biphasic region. You guys notice that? No? The lines on the pressure temperature phase diagram turn into like space on the volume temperature phase diagram. You've got your little dude, yeah, get it out, yeah.
That's like the little dome region.
Yeah. Here, let's let Liesl see it too. There we go. All right, so here, let me get it right. So this is your typical pressure temperature phase diagram, right? Where you've got, there's your pressure or your solid gas line, your liquid is here and your gas is over here. So if we turn it this way, you get the, let's see, this is pressure volume, right? And there's actually a region where you can have like solid and gas, or liquid and gas, or a solid and gas present, right? And that's because like as you change the volume, you're going to, slowly change either the gas into the liquid or the liquid into the gas, right? And then, of course, there's the same kind of thing with the volume temperature, right? So here's volume temperature where that's volume, that's temperature, and you have this region where you can do that. So that's the case for these mixtures. And you have these, regions where you can have different quantities of the gas and the liquid phases present. Okay, we're going to quantify that, but we can't do that right now because we're out of time. It's 11:09. All right. Okay, Liesl, we look forward to hearing your new PR when you come back.